Oh, there we go. Compared to last quarter, this will be the simplest version of this ever. AC resistive circuits. Chances are, every time I have this lecture, I kind of lose my patience with the simplicity of the material and end up getting into things I probably shouldn't get into. But hey, that's life. That's probably what's going to happen today. Okay, basically, when we talk about AC resistive circuits, we're really just talking about everything we did last quarter, because what we do with most situations is we represent the voltage source a little bit differently, and we'll put down 20 volts AC. Okay, now last quarter we would have said that the voltage across the resistor is equal to 30 over 55 times 20. And the voltage across this resistor is equal to 25 over 55 times 20. So what is this, about 9.8? No, it has to be more like 10.8, maybe 11. I'm just going to say about 11 and about 9. Somewhere in that area.
10.9.
I'll
11.
stick with, if it's 10.9, I'll stick with my original answer. So 11 volts plus minus 11 plus minus 9. Add them up, they equal 20, right?
Mm-hmm.
Okay, this quarter we would look at this circuit a little bit differently, and I think that's really the purpose of this discussion, is to kind of take the new material that we've learned this quarter and apply it to what we did last quarter. So let's rewrite everything, exactly the same numbers, but we're going to rewrite it using the terminology of second quarter. Here's our AC waveform, and we'll say that that is 20 at an angle of 0 degrees. This is 30 plus J0 ohms, or 30 at an angle of 0 degrees ohms. This is 25 plus J0 ohms, or 25 at an angle of 0 degrees ohms. Okay, we can even do the same math we did just prior, and we can say that 30 at an angle of 0 divided by, we'll have to add these two together, that gives us 55 plus J0, which is equal to 55 at an angle of 0. Times 20 at an angle of 0. And this one, 25 at an angle of 0 divided by 55 at an angle of 0 times 20 at an angle of 0. Okay, the fact that it's at an angle of 0 means all of our vectors, everything that we have in this entire circuit is all Vs, VR1, VR2, all on the same axis. So there's no angles, there's no sines, there's no cosines to play with. We're dealing with the situation here where the sine is equal to 0 and the cosine is equal to 1. Angle of 0 degrees. Okay? So really nothing's changed from what we looked at last quarter. The only thing that's different is how we represent the numbers. And indeed, we're able to approach this as a DC type of problem because this number right here represents what?
X, RMS.
RMS, or an average over time. So it's almost like working with DC. Okay? That took all of what, 4 minutes?
Yep.
Is that about how much time we spent on that?
Yep.
See, you did learn something last quarter. We would have had to spend longer on that. Is that DC or AC?
AC.
Assuming that this is time and this is voltage. What'd you say?
AC.
AC? Is this DC or AC? Assuming that that repeats over and over again, has a period. What do you think?
I think maybe it could be both.
Can you justify that?
I think if it was DC, there would just, it can be DC because there's still, I don't know why.
Variation? Because how about, let's do an easier one. How about this?
AC.
AC? Why? Oh, it must be my phone. Is that my phone? Got a new one.
It's a sinusoidal wave.
Well, you're not right in this case. What was that?
Somebody sneezing.
Gesundheit, Don. Was that you? Sounded like you. Okay. Above the 0 volt line, everything goes in this direction. Below the 0 volt line in terms of current, everything goes in that direction. So in order to really be considered alternating current, it must cross the 0 volt line. So this is not really AC, it's an AC waveform, but what it is, in this case, is a certain value of AC with a negative DC value added to it. Okay, so you're getting DC plus AC in this circuit. And we're going to see that in third quarter when we look at transistor amplifiers. We're going to see that we have DC and AC. There's an easy way around that, And that is, if I have a combination of DC and AC, something like this, that gives me an AC signal and an affiliated DC level or offset. What can I do about that? You are going to learn something from this. It sounds like I've gone wacko, but you are going to learn something from this. How can I get rid of that DC offset?
The more DC offset go in the opposite direction.
Oh no, we're not gonna solve a problem by adding another problem to it. We're going to remove that. And I think you know the answer, because I know you know the answer, but you're just not seeing it right now. And the answer is, put it through a capacitor. What does a capacitor do?
Charge and discharge.
It allows AC to pass through it and blocks DC. Remember, the capacitive reactance, remember that formula we have? So at a base level, a capacitor allows AC to go through it because it's higher frequency. But to a lower frequency, in other words, if they put a 0 here, then the reactance of that cap is infinite. So none of the DC should be able to get through, barring any leakage. So what that does for us is, over here, after the capacitor, what I'm going to see is the AC waveform centered on 0 volts by removing that DC component. This is something that you've probably seen, and it may look like I'm drawing a smiley face with a tongue hanging out of it, or a tooth. But what that is the DC setting on your scope versus the AC setting on the scope. Okay, so when you move that switch, and then of course the middle is what? Ground. Three-position switch that you have on the scope, that's what the three-position switch does, is it gets rid of the DC component. And the reason that that's important is when we look at something like this, let's consider this waveform. We have here a nice squiggly little waveform that is 1 volt in amplitude with a 50 volt offset. And let's even make it worse. Let's make it even worse. 1 millivolt of AC sitting on top of this great big wall of DC voltage. Okay? How am I going to view that on the scope? Well, I'll make it 5 volts per division. And that'll give me what? 0 volts, 5 divisions. I will see a flat line here at, now wait a minute, not 5 volts per division, must be 10 volts per division. 5 divisions, I got a flat line. Okay, how big is 1 millivolt on this magnification? If this represents 50 volts on my screen, do you think for 1 minute that I'm going to be able to see that 1 millivolt? Okay, so, okay, well, we can't do that, so let's put it on 1 millivolt per division. If I put it on 1 millivolt per division, here's my 0 point, and at the top of my screen I'm at 5 millivolts, my waveform is up in the sky somewhere way up there. So there's no way for me to look at that waveform unless I move the switch to AC and get rid of the DC. And then that will bring that sky-high waveform down and give me my 1 millivolt per division because the DC has been eliminated. Okay? That's one of the things that you're going to have to come familiar with next quarter when you start working with the transistor amplifiers, because that's what you're going to see. You're going to see combinations of AC and DC in the same circuit. Okay, any questions? One more thing that I want to explain before we finish up. This pen has got to go. Keep picking it up. Let's look at the same circuit that we looked at before. And this will almost just be a comment in passing because it's a fairly simple concept that we're going to look at here. But the difference is we're going to make this 20 at an angle of 38 degrees. Okay? So now we're going to have a slightly different problem here. Okay? But what are we going to do with our two resistors? This is 50, or what was it? 30 at an angle of 0 degrees, and 25 at an angle of 0 degrees. Right?
Mm-hmm.
What does that mean with regards to our vectors?
There's a difference in the angles?
Well, there is a difference in the angles, but what is that going to, how are we going to proceed with this calculation? Can we still say that the total resistance is 55 at an angle of 0? Is that still true?
Yes.
Sure. We didn't change the resistors at all, did we? So the current, I, is equal to V over R, which is 20 at 38 divided by 55 at 0. Okay, so the angle, if you notice, we'll do the 20 divided by 55, and that gives us our current. But that will end up at an angle of what?
38. Because you subtract the angles when you divide.
That's right, so it'll be 38 minus 0, right? So that means our current then will be whatever that is, 20, what's 20 55ths?
Almost a third.
0.36.
0.36 at an angle of 38 degrees amperes. Okay? Then we can take these and determine what our voltages are. V is equal to I, which is 0.36 at an angle of 38 degrees times 30 at an angle of 0 degrees. 38 plus 0 gives us 38 degrees. And 30 times 0.36 is what? 10.8?
Yep.
So what happens is everything has an angle of 38 degrees. So all of our vectors now look like this, whereas before they were on the x-axis. Okay, so the angles follow the source in this case if we're simply working with resistors. When we start to work with capacitors, that's when we'll start to see, and inductors, that's when we'll start to see things start to separate over here. Okay, one other thing that we can do just for fun, and I do this all the time to try to make things simpler, because sometimes you get things all skewed up and you've got all these different angles over here, and sometimes what it's fun to do is to just get to 38 degrees and keep in mind that I owe you 38 degrees and just put a 0 in there. Do all the math and then put the 38 degrees back into all your answers. Okay, sometimes that makes life easier. If I have a situation where I have a 90-degree angle here, and this is 38 degrees, and this is whatever that would be, 128 degrees, and I've got something I want to figure out what that point is there, resolve those two vectors. Sometimes it's easier just to subtract the 38 degrees and approach it like this. Get this point, and once you've gotten R at whatever angle you have here, add the 38 degrees back in. It makes it easier than having to deal with these two things separately, both of them having an XY coordinate. Make it simple. Rotate the entire, and that's called rotating the axes. We're actually rotating the axes to meet the drawing. But from our perspective, we're just laying it so that it's nice and flat and even, so we can do our calculations with 0 and 90 numbers. Okay? That means we're just dealing with apples and just dealing with oranges individually instead of having to combine the two. All right? So that's pretty much all we have for today. I kind of went above and beyond the simple AC idea, but I think it's always a good idea to see sometimes when you look at the scope why it functions a certain way, how it functions a certain way. Any questions?
What's your meaning of AC?
My definition of AC is anytime the current actually, or the polarity has to reverse.
Anytime the polarity reverses?
Anytime there's a periodic reversal in polarity that happens over and over again, then that to me is AC. It has to cross the 0-volt line or the current is not really alternating. Does that make sense? Chloe, you have any questions? Anybody? Whatever? Good, well then we're done. I get to move on to what? What's next on the schedule?
126.
Nah, next on the schedule, today's Monday, is 1:40. That comes at 8:30.
Oh, okay, 140. That's not us.
That's not you. I think you guys are done for today.